Okay, we are at, I lost it. We are at section 7.5, kinetic energy and the work kinetic energy theorem. So let's share the PowerPoint, and we'll start here. We're moving a mass, a box, with initial velocity indicated by the red arrow and final velocity indicated by the larger red arrow, a distance of delta x. So the work is the integral from x initial to x final of the sum of f dx. And so working, the force, of course, is equal to mass times acceleration. So as we proceed down this equation, we can see that the acceleration is dv over dt, and of course, velocity is dx over dt. So we have dx dt, dv dx dx. So that's equal to the integral of from the initial velocity to final velocity of mv dv. So the work is equal to 1/2 mv final squared minus 1/2 mvi squared. So the kinetic energy is equal to 1/2 mv squared. And the work is equal to the change in kinetic energy. In other words, the final kinetic energy minus the initial kinetic energy, that's equal to delta K. Well, quite often, the initial kinetic energy is 0, so it just ends up being 1/2 mv final squared. That's not always the case, but that is the case often. So the work is equal to the change in kinetic energy when work is done on a system, and the only change in the system is in the speed of its members. The net work done on the system equals the change in kinetic energy of the system. W equals delta K. Okay, a dart is inserted into a spring-loaded dart gun by pushing the spring in by a distance x. For the next loading, the spring is compressed a distance 2x. How much faster does the second dart leave the gun compared with the first? Is it 4 times as fast? 2 times as fast? It's the same, half as fast, or 1/4 as fast? Well, the fact that there's a v squared, you would think it would be 4 times as fast, but actually it's twice as fast. Oops. Let's click here, 2 times as fast. Now, that may seem a little confusing to people, so let me show the equation, how we got there. And there's, let's share the iPad, and I'll try to remember to post these. Let's see, there we go. There we go. Okay, so we see that the work is equal to 1/2 kx squared. That's the work to compress the spring. And the it's also equal to 1/2 mv squared. So we can equate those two. 1/2 mv squared equals 1/2 kx squared. So you get rid of the 1/2 on either side. So mv squared is equal to kx squared. So the velocity is equal to the square root of kx squared over m. Oops, I have to control it from here. So v1, we've moved it x. So v1, the initial velocity, is equal to kx squared, the square root of kx squared over m. Now v2 is equal to k, the square root of k times 2x squared over m. So that's equal to the square root of 4kx squared over m, and the which is equal, the square root of 4 is equal to 2. So that's equal to 2 square root of kx squared over m. And you can see that this, whoops, wrong one. Let's change that to this. This and this are the same. So v2 is twice the velocity of v1. So there's an explanation of why it's double. I think that's the end of the quick quiz are usually the end. So let's see. Yes, next we're gonna talk about potential energy of a system. So that's it for right now.